Jai Hind, welcome to class of Analog and Digital Communication. We'll start from where we have left. So we were discussing about analog modulation or continuous wave modulation. So we know that analog modulation or continuous modulation is a kind of modulation where the message signal used is analog in nature. When my message signal is analog in nature, this has to be a continuous wave, so it is also called as continuous wave modulation, where the wave is a function of time. Here my sine wave is, I can take the wave as sine wave or the cos wave. So here my sine wave can be represented by three parameters. If I consider my message signal to be a voltage signal, I may represent it as xt or mt or vt, right? Let's suppose I have considered it as Vt. So my Vt is A sin omega t plus phi, where this is the amplitude part and this complete part is my angle, right? So I can say that in totality it has two parameters, the amplitude and the angle, or if I elaborate this angle, then it has frequency and phase, as my omega is 2 pi f, right? So this complete is the phase angle plus minus of some variation, that is my phase variation or phase deviation. If this has this would have been a pure sinusoid, then the phase variation would have been 0 here. But as I am representing it with some plus minus of phi, that means it shows some deviation from the actual phase. So this is not a pure sinusoid, there is a phase variation for it. So sine wave is described by three parameters, that is my amplitude, frequency and phase. Let the signal be Vt, right? I won't consider it to be carrier here, I will consider it to be the message signal here. So we can have amplitude. So depending on what parameter of my carrier wave varies with respect to the message signal, the name of modulation is given as per it. So if I vary the amplitude of my carrier wave with respect to my message signal, then this is called as amplitude modulation. If I vary the frequency of my message signal, that is called as frequency modulation. If I vary the phase, then that will be called as phase modulation, right? So I do have three kinds of analog modulation or continuous wave modulation. Frequency and phase modulation are combiningly known as angle modulation, right? Let's start with amplitude modulation, the very first kind of modulation. So in amplitude modulation, the amplitude of my carrier wave is varied in accordance with the instantaneous value of my modulating signal or message signal or information signal, right? My modulating signal is also called as my information signal, my message signal, or the intelligence. Right? So here we do vary the amplitude of my carrier wave with respect to instantaneous value of my message signal, keeping its phase and frequency constant. Let's suppose I represent my carrier wave with notation Ct, so that we remember it. As my message signal that I consider will always be a voltage signal, so it will be easier for me to denote it as Vt, right, as I have represented in the previous slide, right. Let this be the message signal, right. and my carrier wave would be represented as Ct. Ct will be equal to Vc cos 2 pi fct plus phi. We have elaborated the term omega here, omega is 2 pi fc, right. So Vc here represents the amplitude of my carrier wave. In cos of, as the wave I have considered is a cos wave, so it will be 2 pi fc t plus phi, right. This is the complete phase angle where this represents my phase deviation or phase variation. If it is not a pure cos wave, then there will be a little variation from the actual initial phase, right. Modulating signal or the message signal is represented as Vt, which can be elaborated as Vm cos 2 pi fmt, where my Vm is my amplitude of my message signal, and here frequency of message signal is f subscript m. Here the frequency of my carrier wave is f subscript c. We have to take care of one thing here, that if we talk that my message signal is an audio signal, then its frequency would be lying between 20 to 20 kilohertz, 20 hertz to 20 kilohertz. Whereas the carrier that I used, we know in most of the radio wave communication my frequency varies from megahertz to gigahertz range. So the frequency shifting that will be followed is from hertz or gigahertz to megahertz to gigahertz, right. The actual message signal will be of the range falling in hertz and kilohertz, and it will be shifted to megahertz and gigahertz. That is the frequency of my carrier wave. Here the information is contained in the envelope. Now what is envelope, and we'll be studying about it, right. See, this is how my amplitude modulated wave looks like. If this is my message signal, and let's suppose I draw a carrier which would be a very high frequency wave. We can see from here one complete cycle takes this much time, and here at least 1, 2, 3, 4, approximately 10 cycles of the carrier wave passes. So we can see that frequency is 10 times, but actually practically it is 100 times or 1000 times, because we go from 10 to the power 3 to 10 to the power 6 or 7, right. So it is basically 1000 times or even higher, but it is impractical to show it here. So we are representing it with a visually understandable signal, right, because one signal, one cycle can be compared with 10 cycle. It will be very difficult to draw here 10,000 cycles in one cycle of my message signal, right. But practically we need to understand that the frequency shifting occurs from hertz and kilohertz to megahertz and gigahertz range, right. So what basically happens is, according to my considering my message signal as the voltage signal, the amplitude of this carrier will be varying. And how does it vary? We see that this is a continuous wave and the amplitude is continuously rising. As the amplitude is continuously rising, the amplitude of this carrier wave will also be continuously rising, keeping its phase and frequency constant. Like it starts from 0, it starts from 0, rising, rising, okay. Number of cycles per second kept similar, right. So phase and frequency being constant, its amplitude will rise when the message signal rises, and amplitude will fall. I should be drawing it with a dotted line, and the amplitude will fall when it is minimum. So here we can see at this point the amplitude should be maximum. Let's draw a reference. I've drawn the reference. So see, from here to peak, it reaches the maximum amplitude when amplitude of my message signal is highest. So which parameter of my message signal I am considering here? I am considering the voltage of my message signal. So message signal is always a voltage signal here. According to the amplitude of my message signal, the amplitude of my carrier wave is varying here, and the phase and frequency of my carrier wave remains constant, intact, right? So its amplitude rises when the amplitude of message rises, it reaches its maximum point. When it falls to minimum, it also falls to minimum. We can see this is the minimum height in positive and negative direction. So this complete is peak to peak. So this is called the envelope of my AM wave. So in the previous slide, as we were talking envelope, this is the envelope of my AM wave. The envelope contains the information. What does it mean? See, the primary reason of doing modulation was to enable my signal to travel long distance, right? But as I cannot do alteration in the actual message signal, if I change the actual frequency of my message signal, the essence of message will be lost. So what I do? I make it board on a carrier. So physically it doesn't board the carrier. We give two inputs to a modulator box, and what do we get in output is a modulated wave. This is the modulated wave, right? Here somehow the carrier takes the identity of message signal, and here where is the identity taken? In the amplitude. Because at receiver, if I draw a circuit intelligent enough to read the peak values of the message and plot the wave, reading the peak value and plotting it back will retrieve back my message signal. So this is actually what modulation is. We do not transmit this, we change this and we transmit this and we retrieve this. Purpose is solved. So this is what modulation is, and this is the picture for amplitude modulation. I hope this makes sense. Now modulated signal, how can we represent it? My modulated signal is represented as, here we may use some other notation as well, like ST, as VT we have used for message signal. T equals to VC cos 2 pi FCT into 1 plus M cos 2 pi FMT. If what basically happens is, to its amplitude this is added and this is subtracted, right? So we simply do trigonometric applications here. We add in the envelope part, in the amplitude part, we add the signal. So we have the equation for these two signals, right? This and this. We apply trigonometric functions, and the output that we get is the resultant for my modulated wave. And this is my modulated wave. Here my VC is the unmodulated peak carrier amplitude, true. It is the amplitude of the carrier. When it was unmodulated, it was VC. Here also it is VC. FC is the carrier frequency, true. FM is the modulation frequency or modulating frequency or message frequency or information frequency, true. Here we get a new term which is small m. We need to understand this. This small m is called as modulation index. I'll discuss about it, right? This is also defined as degree of modulation. M must be lying between 0 and 1. What does it mean? Let's talk about it. If M is greater than 1, it gets over modulation. Let's see what it is. So one thing we can see here, this modulated signal mainly consists of the frequency, which is my carrier frequency. So frequency shifting has occurred here. The modulation index of an amplitude modulated signal is defined as a measure or extent of amplitude variation. How much variation in amplitude has actually occurred, that is my modulation index, and mathematically it can be expressed as a ratio of modulating signal amplitude by carrier amplitude, where VC is the carrier amplitude and VM is the message signal amplitude. It describes the amount by which modulated carrier envelope varies with the static level, right? True. Using the equation, this equation Vm by Vc, it can be seen that modulation index of 0.75 means that signal will increase by a factor of 0.75 and decrease to a factor of 0.25 from its original level. A modulation index of 1 is the maximum level of modulation that can normally be applied and occurs when the envelope increases by a factor of 1. I'll show you the picture. If modulation index is below 0.5, below 1, how does my envelope looks like? If it is above 1, how does it look like? The amplitude modulation depth figure is complementary to the modulation index, right? True. Typically, the modulation depth is the amplitude modulation index expressed as percentage. So, that 0.5 we represent as 75%. In reality, the terms AM modulation index and the AM modulation depth are often used interchangeably, so we can call it as modulation depth or modulation index, right? Small m and represented by small m and usually represented in percentage. When represented in this decimal, we represented by small m, and when represented in percentage, we usually denoted by capital M. It's just simple denotation. See, if this is my message signal, this is my carrier signal. This is how my wave will look like when the modulation index is less than 1. This is how my wave will look like when my modulation index is equal to 1, and this is how it will look like when it is over modulated. Let me draw so that it will be clear. If this is my message, this is my carrier, my under modulated wave will have such kind of envelope. In case of 100% modulation, my V min reduces to 0. Sorry. So, my V min reduces to 0. In case of over modulation, what occurs? We get such variation, that is phase reversal. We can see here there occurs a phase reversal. So, this is the case of small m less than 1, this is small m equals to 1, this is small m greater than 1. When my small m is greater than 1, then it reverses the phase, right? See, here we can see the phase reversal. This is another formula for my modulation index, that is either I can have small m equals to Vm by Vc, or I can write it as Vmax minus Vmin upon Vmax plus Vmin. What is my Vmax here? This is my Vmax and this is my Vmin. This is my Vmax and this is my Vmin, right? Vmax minus Vmin upon Vmax plus Vmin. If I talk about the spectrum of my amplitude modulated wave, modulation produces two new components which are called as sidebands, and sidebands have frequencies either above carrier frequency and little below the frequency. Bandwidth requirement for AM, bandwidth equals to twice of the maximum frequency content of my message. This we should be knowing. Spacing in frequency between carrier and sidebands is equal to the modulating frequency. Let's see. If this, I represent the amplitude spectrum like this. With respect to frequency, this is my carrier frequency. So, a little lower than the carrier frequency is called as lower sideband, and little higher than the carrier frequency, that is called as upper sideband. So, this is how spectrum of my AM looks like. How do we get it? When I expand this is the waveform, the equation for my modulated wave. When I expand it using trigonometric relations, what do I get? Vc cos 2 pi fct, a pure component of my carrier, and because of the cos relations, plus and minus, half of 1 by 2 Vc cos, when we have cos into cos, cos A plus B plus cos A minus B. So in minus case I have Fc minus Fm, in plus case I get Fc plus Fm. This is called as my lower sideband and this is called as my upper sideband. See, the lower sideband has frequency slightly lower than my Fc because my carrier frequency will be in megahertz and gigahertz and message is in hertz or kilohertz, right? And upper sideband frequency is slightly higher than my carrier frequency. So the frequency is oscillating around the carrier frequency only. So we call it that frequency remains constant, right? This expression consists of 3 sine waves at frequencies of carrier, lower sideband which is Fc minus Fm and upper sideband which is Fc plus Fm. Fc is my carrier frequency here. For a fully modulated wave, if I consider the perfect modulation case, the 100% modulation case where my small m equals to 1, then 2/3 of the power gets wasted. How? Total power can be given by this expression, Pt equals to Pc into 1 plus m square by 2. And when I put the value m equals to 1 here, my Pc will comes out to be 66.66% of the total power of Pt, right? So from here I get to know one point, that when I transmit my amplitude modulated wave, 66.66, that is 2/3 of the power gets wasted in transmitting the carrier and only 1/3 of the power is consumed by the actual information, and the actual information is contained within the sideband, that is upper sideband and lower sideband, which is 33.33%. So from here I can call that AM has efficiency of 33.33%, which is quite less. So this leads me to go for another kind of amplitude modulation variation which is called as double sideband suppressed carrier, which we will be talking, right? So one drawback of AM, it is bandwidth inefficient and gets affected due to noise because information is contained within the amplitude and there are higher chances, higher probability that noise will be affecting the amplitude or envelope part. So these are the variations of AM. If I want to save my power, I will go to double sideband suppressed carrier. So what is the first thing? Double sideband with carrier. It is also called as double sideband full carrier. So in some books you will find the term DSB-FC. So this is the normal AM or conventional AM. So it is also called double sideband with carrier, double sideband full carrier or conventional AM, which we have just discussed. These are the variations of AM which are somewhat advanced. In what way? We just discussed how AM is inefficient in terms of power. So when after modulation I suppress the carrier and transmit only the sidebands, I am able to save that 66.66% power. So that kind of AM variation is called as double sideband suppressed carrier. We will be talking about it in detail in next classes. This is for power saving. This is for power saving, and we know that lower sideband and upper sideband both contain similar information because both are the mirror images of each other. So why to send both the sidebands? Just send one sideband, and now if I want to save this bandwidth, I'll send only one sideband. After even suppressing the carrier, I'll send either lower sideband or the upper sideband. So this is for bandwidth conservation, right? Another variation of AM is called vestigial sideband, VSB. This is for easier implementation of my filters. When I do SSB transmission, there comes some filter limitation which we will be talking in detail. So vestigial sideband is for better designing, practical designing. So for power conservation we go to this, for bandwidth conservation we go to this. So the sideband carrier has like in the previous slide We have discussed this is the carrier power. So these are some advantages that we have already discussed about AM. Simple to implement, right? It is a conventional cheap kind of modulation. If I talk about disadvantages, it is bandwidth inefficient, it is power inefficient, and it has high level of noise, as most of the information is contained within the sidebands. These are the references. Thank you.